device that you are going to use, the analog oscilloscope, is a pretty simple device, though it looks complicated with all these knobs, right? So what my objective for today is basically for you to understand how this works and what all these knobs are, so that you are not intimidated by this device, and this is there for you just to make your life easy, to make correct measurements. You need to understand how this works in order to make correct measurements. This is a measuring device, right? So that's the whole purpose of this. Now, oscilloscope, now you have these fancy digital ones with all sorts of digital signal processing and AI and all sorts of other fancy things embedded. But in its core, it's a very simple device. All what it shows on the screen is how the voltage varies with time, and that's what you see here, right? So it's, well, this was invented way before the LCDs were invented. So therefore, this is a very kind of ancient technology in terms of that. So therefore, that's why this is important. We are going with this LCD rather than going with these new ones. We are going with this. You guys can hear me, right? If you don't, please come up. It's okay. You guys can come up. Later on, you can go there, but you guys can flock around here if you don't hear me, right? Because right. Anyways, so what I'm going to do is I'm going to show these things on this scope. So since you guys cannot see what I'm doing, you can see it on this with this webcam. Right. So I also want to show you this. So what I would do is I would turn this like that, so that you can see the blackboard also, right? Okay, so let me start with the blackboard. So inside this oscilloscope, what you have essentially is a cathode ray tube. You probably have heard of cathode ray tube from your A-level class. How many of you have cathode ray tube? Don't worry, just raise your hand up so that I can see. You guys know each other, as I said, right? Okay, there are few who has not, so it's a binary thing, right? Some have heard of it, some have not. Okay, but it's what you have in this, in a sense, an electron gun. Now, the purpose of this thing is to generate a trace which changes with time according to the voltage applied to this probe. Okay, so that's the purpose. In order to get that, at the time this was invented, what it does, this cathode ray is used in many applications. So you have a cathode. It's typically something like a nickel or some metal like that. Now, when you heat an element, the electrons inside that element, they get excited, right? They go into a higher energy level. So absorb that heat and go into a higher energy level, right? So the higher the heat, the more energy electrons absorb, and they can actually jump out of this metal, and they just form a cloud around this thing. So in order to do that, you have to heat this up. So what we do is something like a heater, something like a tungsten or some material, a filament, and then you send a current through it so that it heats it up. Doesn't touch the cathode, this nickel cylinder. So when it heats up, it emits electrons. Now there are free electrons lying around. Now I want to create an electron beam, right? That's my objective. So in order to do that, you need to accelerate these electrons in a particular direction, right? So what I'm going to do is I'm going to apply an electric field. How do I going to these electrons are negatively charged. So in order to accelerate in some direction, what kind of a field you have to apply? You have to apply an electric field so that it gets attracted, right? So I put a let's say anode, another metal electrode, and I apply a large voltage. So this side has to be positive, right? So that electrons will get attracted. So typically this is about, so what happens is, typically this is like the ground. And so therefore, in order to make sure that there's a large electric field, this is somewhere around minus 2000 volts, 2 kilovolts. Minus. Okay, so with respect to this is positive to 2000 volts. So typically this side is grounded. Okay, so what happens is electrons get attracted here, right? So so you have free electrons and then an electric field, they get accelerated towards this electrode. Now we form a small slit here, so this is a hole in this electrode, so that some electrons that gets attracted here, some basically they just go here and they get absorbed by this electrode and send it back to the cathode and completes the cycle. But some electrons, they escape through this hole. Now we shield this so that electric field is no longer applied onto this, otherwise it will get attracted back to that, right? Something like will go back and come back like that. So we apply a shield, and no longer now you have this electric field. So because there is no electric field, they just go along the path that they have been going. There's a small aperture, so maybe some may go like this, some may go like that, right? Small cone like that. And you have in front of this tube, this area which is called it's a screen which is plated with phosphorus, right? What happens when electrons hit phosphorus? It absorbs the electron, and the element itself, the electron goes into the next energy level, and it's not stable there. After a while, what happens? It gets back to its own normal stable energy level. In doing so, it releases a photon. It releases the quantum of energy between those two lines, which happens to be this green color photon. Okay, so one electron, one photon. It releases like that. But when you do this produces a lot of electrons, right? So therefore, there is a beam of electrons which hits this phosphorus layer, which releases these photons continuously. Now, one thing about this is, this phosphorus, as soon as they absorb it, they all don't come down at the same time, right? So maybe there are 100 electrons absorbed by 100 phosphorus atoms, and they don't all release these photons at the same time. It takes some time. There's typically a bell curve like this. It takes some time. Some are released very fast, some are released later. So because of this glow that you see, this glow that you see on this screen, right? You see this glow. So if I do this, if I reduce the intensity, that's one of the knobs that you see, which is called intensity. So you can increase and decrease the intensity. What do we do by this actually is, I am controlling the number of electrons that are coming out of this. This is done by a mesh that is around here. There's a mesh here which basically absorbs some of these electrons. By controlling the voltage on that mesh, I can actually decide how much electrons actually go past this mesh, right? And thereby you can control what is the intensity of that. Okay, so and also if you just do that, there will be a cone like this. And if you really increase the intensity, you can see it's kind of like a shadowy like circle on this. But actually what we do, if you, there's another control here which is called the focus. If I turn this, you can see I can control the size of that circle. So this is focusing, right? So this is done by applying another electric field, right? This is also another electric field, negative electric field, so that it bends it like that. So this is called focusing. That if you have a negative electrode here, what happens? It will repel the electron, right? So therefore, it basically bends the beam, and you can, by controlling the voltage, you can make a sharp point on the screen, right? So it's kind of like that's kind of like the. Now I'm going to reduce the intensity. So here, on the screen you can't see any difference, but you guys can see, right? See, focusing and not focusing. You can switch on the oscilloscope if you want and try this while I'm demonstrating. Okay, so you can see, you can make it focus. This is done by applying the voltage onto this electrode, focusing electrode, right? So now you know how to generate one dot on the. I have put it into XY mode. That's why you see the dot. Okay. You may not be able to do all what I am doing because you don't know the controls yet, but it's okay. You just keep it on and try to control. Even if it's a line, that's fine. You can still control the intensity and focus it, right? So you can still do that. You don't have to necessarily put it into XY mode. So, all right. You can do it next time when you're actually doing the practical, but pay attention to what I'm saying right now, because otherwise you will miss it. Okay. So now you know how to generate a dot on the screen. Now you need to control this dot, and you know also that dot, how long it stays. So, for example, if I put it like this, you see, the glow stays there for some time. Okay. If I see the length of that small thing that you see there, it's kind of like the duration it stays on, right? That's how long it produces this. If I increase the intensity, there will be more, and you can see that there's another property called persistence. How long it produces. So this is like persistence is like the width of that bell curve. How long? This is like it's releasing energy immediately. This is it glows for some time, right? So there are some oscilloscopes, not these, which can actually control the persistence of it also. Especially the new ones, the digital ones, there is a control which controls the persistence, though in order to simulate this effect, right? Right. Anyways, so this is what happens. So now my objective is to control it on this screen. There are two dimensions, up and down and left to right. Now if I want to control it left to right, this direction, right? So in this direction, what do? I have to apply an electric field this direction, that is horizontally, right? So that it gets deflected in that direction. So therefore, I have what I call this horizontal plates. These are like electrodes that are like this, right? So they are parallel electrodes, and the electron beam goes past that. Okay. So by applying a voltage between this and that, you can control where it hits on the screen, whether it is here or here, right? Say for example at 0 volts it hits here, plus 1 volts it hits here, 0 volts, 1 volts. You can control it like that, right? So each position corresponds to one single voltage, right? So that is what you do here. Okay, so you have something like that controls this. This is actually Okay, so that is the horizontal control. Now if you want to move it in vertical direction, similar to this, you have to apply, so let me get rid of this beam now, and I'll just draw one beam to make things clear, right? So you have the horizontal plates, and then you have the vertical plates. By applying voltage between this and that, Vx, we call this Vy voltage, right? By applying this voltage Vx in x direction, sorry, y direction, so this is x, this is y. Y direction, you can deflect it top to bottom, right? So I can focus my beam anywhere on this, but it still will be a dot. Depending on the value of Vx and Vy, this point, again, this may be 0 volts, this may be 1 volt in the y direction, Vy, right? But controlling Vx and Vy, I have a one-to-one mapping on this screen, correct? So now the question is, how do you see this, these lines? In order to do that, all what you need to do is, with time, you need to change the Vx. With time, you have to change. So if I apply something like this, a ramp signal, this is 0, this is 1 volt. What will happen? It will go through it will move through the screen, just like what you see over there, right? So this is exactly what is happening inside this right now. There is no voltage applied on the Vy Y plates. That is why it's on this horizontal, the 0 line, right? But it moves on this horizontal line, which means you are repeatedly applying a signal like this, repeatedly applying, right? So it's like a sawtooth. So it goes from here to here, comes back, goes there, comes back, goes there, comes back, right? That's what you have. But when it comes back, do you see the signal? If I apply this particular signal, it should also show a line coming back very fast, going back, right? Going front slowly, coming back very fast. That's what you should see if this is what actually is happening inside. But during this side, during this, we call this flyback, coming back, flyback. During this flyback, we apply a very large negative voltage, so that the signal, negative voltage means in y direction. So while it is coming back, it's coming back, but the signal may be somewhere here, so you don't see it, but it is there, right? So it's going there, going down, coming back, right? So that's what's happening during that. So this is there, but you don't see the signal during this flyback period. This is called the sweep. Sweep, you see it. Now, how fast you want to go from this end to that end is decided not by the voltage. Voltage is fixed. One point is 0, the other point is 1 volt. For example, it could be different voltage actually, but let's assume, right? 0 or 1, right? So if you want to go from this left to right very fast, all what you need to do is change the slope of this, right? So this is what we do using this time-based signal. This large signal knob here, the time per division. There is something called time per division right here. You see, it's called time per division. If you change it, you see, it gets faster and faster, right? See, it gets faster and faster until one point you don't see any movement. Right? Now you don't even see the line going, right? Because our eyes, there's a particular frequency beyond which you can't see the changes, right? So you keep increasing, now you don't see it, right? There's a particular frequency and now you kind of see it going, but beyond that you don't, right? So this is basically all what you do there is adjusting the sweep. How long it takes to sweep through this line. So therefore, let's assume for the time being this is 1 volt. Now there are how many big squares there? 1, 2, 3, 4, 5, 10. 10 big squares there, right? So if I set it to 1 volts per division, 1 volts per 1 seconds per 1 divisions per second. 1 division per second. Now, if there are 10 divisions, if the whole thing span is 1 volts, what is 1 division? 1 over 10. So, right, so you have have 10 such divisions. So this is this is the center line. So you have 1, 0 to 10. So therefore 1 division is, now if I say this is 0 volts and this is 1 volts, 1 division corresponds to 1 volt divided by 10 volts per division. Correct? So therefore, if my time base is set to, let's say, 1 milliseconds per division, on this dial you have numbers 1 milliseconds per division, 1 milliseconds per division. If I have that, that means it will change at a rate, 1 division is 100 millivolts, right? So 100 millivolts per millisecond. This slope is 100 millivolts per millisecond. So one whole thing is 1 volt. It will take 10 milliseconds. 1 volts per 10 milliseconds. So the slope actually is 1 volts per 10 milliseconds. You can figure out that slope, right? By changing the slope, you can change the sweep rate. Depending on that, it changes the time. So in this case, this is 1 millisecond. If I change this to 10 milliseconds per division, so that means this 1 division becomes 10 milliseconds. And it takes how many seconds for this to sweep from this end to this end? 10 such divisions. That means 100 milliseconds. If this is 1 division is 1 second, then it will take 10 seconds to sweep, right? Say for example, if I put it into this largest value, which is 0.5 seconds per whole, 0.5 seconds per division. So to go sweep one of these, it takes 0.5. The whole time it takes is 5 seconds. It will take 5 seconds to sweep from one side to the other. You can count and see, right, how long it takes. So that is basically, now you know how to control this. This is nothing but you are controlling the slope of the signal. So there is this time per division knob that you have on this, right? It's basically a variable resistor or something like that. It tells me to change the slope, right? Change the slope of this, and that voltage is given there. So this is basically this is a sawtooth generator, right? Triangular wave generator. It sends a voltage there. So what you see here is something like that. Correct? Everybody understands this concept? It's very important that you understand these things right now. If you have any doubts, raise your hand and ask at any point, because that is why I want to have this demonstration class. Okay? If you have questions, please do ask. Everybody clear about this, right? Yes? I need your feedback, otherwise this is not going anywhere. You guys understand this? If not, please tell me, I will explain it again. You guys understand? Yes? 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 kind of blurred. No, please raise your hand. If not, I will explain again, because I stack things up. So one on top of this. So if you don't understand this, certainly you will not understand the next concept. Anyone who doesn't understand this, raise hand. It's okay. Don't worry. Nobody is going to eat you for raising your hand. Okay. Right. So you know how to sweep it across this. At least this operation now you know how to do and how to control. You understand it, right? You need to understand. By controlling this knob, you can control the sweep. Right. That we see. Right. Now the next thing is, while it is sweeping, now it sweeps at a constant speed. That is very important. If it were, if this was something like this, then it would start very fast but then end up slow. If it was like this, then it will start slow and then so like that, right? No, this is basically going. I'm sorry. It is going at a sorry about that. I keep forgetting. Let's try to have it so that we have both at the same time. I need the controls also same, right? Okay. So therefore this is straight. This is a straight line. That is important, right? Now while it is going like this, what happens if I apply a voltage here? Accordingly it will change its vertical position, right? Wouldn't it? If I apply a DC voltage instead of 0, what would happen? It will jump up and it will stay there, right? So if I apply a DC voltage, what you would do is something like this. Instead of staying in the, I haven't applied physically a DC voltage. What I have done is I have changed the position, X position control right here. This one, what it actually does is applying a DC voltage to this Y control, right? So what it does is basically giving a variable voltage. So this is the Y position. So right here. Right. So now it's basically, by changing that Y position control, I can get it into any place I want. So typically what I do, what you have to do, put it into ground so that you know the signal is 0. I know. So this terminal that you have here, right, this one, so this thing over here, right, what you have outside is connected to chassis. Okay, it's the chassis. It's this outside box. It's connected to that. Inside is this so this is like the ground. This is the point which connects to this amplifier through a so that's this point, and it goes through an amplifier with a gain A, and it gets added to this voltage source, right? It's a DC voltage, so you add these two together and you apply it here. Okay, so that's basically what happens here, and this is then that point. So depending on your choice here, so you have AC, DC and ground. See, these buttons, if you put it in, it's DC. That's DC coupled. That means you are directly, so you have the signal, the probe, right? So you have the crocodile clip. The crocodile clip is basically that crocodile clip that you have is connected to that chassis internally. So that is this point. That's the chassis. That's the chassis that's connected to that. This is the probe. Okay, probe wire, and this tip. That's this one here, right? So that this one, right? So this tip that is there. It's connected here. Now, if it is DC connected, this directly connects to that. If it is the ground, there's this other button next to it, ground, this one, if you press this ground, what it does is this directly put it into this chassis. Okay. So it gets into this. There's another position which is called the AC, right? If you press this first button again, it comes up and it says AC. AC means you have a capacitor like that. So you are connecting it to this probe tip through a capacitor. Later on you will learn that capacitors block DC components. The capacitors, they don't allow DC components. They charge up to that DC value and after that it doesn't change. But AC components, the values that change, they can go through the capacitor without any issue depending on the size of the capacitor. Okay? Right. So that is what happens. So therefore these are the buttons here, right? These buttons basically correspond to these functions. So this button is the ground button. These two are the AC DC if you press and if you not press. Okay. So that's, now you know this one. You know this position control. You also know this time per division one, and also intensity and focus. So intensity and focus, both these, the focus, I have removed this focused one, but still there. So you know the operation of all these now, right? And then this other vertical position knob, what it does is changing the gain of this amplifier. There is a gain here, right? If it is just 1, if the gain, now I'm not talking about time volts per division, not this volts per division, whatever the amplifier, it has a gain. The gain of it is controlled by this, but this, once you change the gain, now I said output can be only between 0 and 1, right? What maps to that 0 and 1? Let's say if I have gain of 1, then 1 volt maps to 1 volt. But if this gain is 10, if this gain inside is 10, when the voltage is 100 millivolts, output will be 1. Correct? Output will be 1 when the input is just 100 millivolts. Right? So therefore, so if I want this range from top to bottom, let's say here is 0, here is 1, or maybe this is 0, this is minus 1, this is plus 1, let's say. Okay, this is 0, minus 1, plus 1. So there are 4 divisions here. So therefore one division is 250 millivolts. Now these are not actual values. Inside this, it can be anything. It doesn't really matter though. Okay, some value, right? So let's say, so this one division is 250 millivolts, just like the time per division one was like 100 millivolts per division, right? So like this, here 250 millivolts per division. There are four divisions from center to the end, right? So that's why we took it like that. So that is, this is 0 for voltage, so y direction. So this is minus 1 volts, this is plus 1 volts. So therefore there are 4 divisions. So one of these divisions is 250 millivolts. Now I want to, now there is something called volts per division. So division is what? Division is 250 millivolts. That you can't change now. Now whatever the value that you want here, let's say now I have put it into 5 volts per division. That means I have to, this should be 5 volts. So if that is the case, when I apply 5 volts here, it should be 250 millivolts applied to the Y plate. Correct? So therefore, now I can calculate the gain as 5 divided by, 250, this is the output, millivolts, divided by 5. So it's a attenuation in this case, but probably inside this, it's not 250 millivolts, it could be much bigger value, right? Maybe from bottom to top, maybe it could be 20 volts. If it is 20 volts, 1 volts to, so it will be just 1 volt. Sorry. So instead of -1 to +1, if this was -20 to +20, let's say, is another example. So one division then is 5 volts. Correct? So in which case, all what we will be doing is 5 volts divided by 5 volts. So the gain will be 1. So the gain of this amplifier I set to 1. I just directly connect it to my Y plate. If I change this to 0.1, right? So right now I have 1 volts per division. Now this is still 5 volts. So when I apply 1 volt, now output is 5. So what is the gain? Gain now is 5, right? Clear? So if I change this to this very small value, the smallest one, it is 1 millivolts per division. 1 millivolts per division. So if I apply 1 millivolt, output will be 5 volts. That is 1 division. So what is the gain now? 5,000 divided by 1. So gain is 5,000. So I have amplified it by 5,000 times. So that's all this does. So the purpose of this the gain controller knob is that volts per division knob. That's all it does. Very simple. Okay, you understand now how it works, right? Right. So there are two such channels, right? There are only one set of these, but there are two channels. So therefore, in order to allow that, I have to have two identical systems like that. There will be another set just like that, connected to another probe, and then you need to make sure which one is connected actually to the plates, right? Only one can be connected at a time. So you decide which one you connect using this mode switch. There's a mode switch that you can see which says channel 1, channel 2, dual and AND. Correct? So what I'm going to erase this because it's getting cluttered. So channel 1, I have the probe outlet. The UNC. This is connected to the chassis, and this is multiplied by a gain. So before that you have this settings, right? Right. So I have this selection, this DC-AC and ground. So DC-AC is this. So this is DC-AC switch, and this is the ground. Ground is here. So if you connect it to ground, obviously you will disconnect this and connect it to ground, so that this is only connected to the ground, not this. Okay. So you see these things here, and then you have this gain controller. This A is set by the volts per division. So this is the A is controlled by the volts per division. A is controlled by the volts per division setting, right? And then you also have an adder which adds this position control, right? It's the position, Y position control. So channel 1 Y position control. This is this one right here, right? So you have that, and that goes and connects to the Y plates. Right, so this is one end, the other end is connected to this. Similarly, there is another identical thing like this. Something similar. This is channel 1. There's a channel 2 just like that. That also has an output. So if I put to channel 1, this points here. Channel 2, it points to here. Channel, and then there's another choice called dual. Dual, right? Dual position, what it does is, it takes both these and switches between 1 and 2. How fast it goes back and forth, 1 and 2, depends on some other settings, right? So what it does is, in dual mode, it swings here and there, not physically, electronically. Because you don't hear anything, right? Tick, 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 you don't hear, right? If it was physically moving, you would have heard something. No, it's through electronics, right? So it is going back and forth between the two traces. How fast you are going to go depends on some other factors. Say, for example, chop. If there's another button called chop, sometimes it's on this mode, on mode selection also, right? In some you have CH1, CH2, alt, chop. Right, these are called dual. So if that is the case, alt means you take you apply the signal during the whole sweep from here to there for one channel 1. Come back, now you apply it for the second channel. Come back, apply it for the first channel. Come back, apply it for the, so the whole duration you are applying only one signal. So alternating, that's why alt means, right? Alternatively you apply channel 1 and channel 2 to the vertical amplifier. There's another one called chop. Chop means what? Cutting, right? Chopping vegetables, you have heard, right? In that, what you do is you apply a little bit of this, a little bit of that, a little bit of this, a little bit of that. So you chop between, so you apply the CH1 and CH2 in a chopped manner. But obviously during this time you don't draw the first channel number 2 because it's not applied. So if you do that, you will clearly see these kind of like broken. So these signals will be drawn like broken lines. Okay, I will show you later. Right. So now you see these are do you see it now? You see chopped mode. So these are two channels. So this is channel 1. Sorry, this is channel 1 and this is channel 2. They are both grounded, but you see the two traces. It's kind of like broken, right? You guys see it? It's broken. Can you guys see? Yes. If you don't see, please come forward. Okay. You have to see this, right? So you see the chopped mode. See? You guys can see? That's the chopped mode. In the alt mode, if you remove it, you see you don't see that. See? You draw one after the other. You draw one and then the other. So you draw one and the other. Now, if you make it like this, it looks like you are drawing both the same time, right? In this mode, what happens is this alt mode applies to fast signals. Fast signals means if this is very short, this duration is very short, you draw one and come back. Otherwise, now in this mode, it's no point doing that. Obviously, by the time you come here, when the volts per division setting is very large, that means it takes a long time, few seconds to draw one line. By the time you come to the front, again to the left side, that line will not be there because the persistence will be much shorter than that. So therefore, that is why in this mode, it's drawn in chop mode anyways. It applies to fast modes like this. So now one after the other, it will draw one after the other. It's fast, you can't see. Now you can see, right? So if you look at this, kind of, you can see, you draw one, second one, right? You can see it clearly, right? When you look at it here, it's more clear, right? But if you increase it, it doesn't get chopped. But if you put it to chop mode, you will see this choppy waveforms. Okay? So if you remove it, you won't see this chopping lines, right? Okay, so that's all-time chop mode. So therefore, this is the dual mode. So you have channel 1, channel 2 dual, and also in some ones you have add function. Add function. In that, what you do is you take both this and send it through a adder. You take both and send it through an adder, and send that combined signal to the add. So that's basically what add does. Also, sometimes there is another one in channel 2, right? So here the invert, see, invert button. So what it does is it sends the channel 2 through an additional inverting amplifier. So it's as if you are multiplying it by -1, right? Inverting amplifier. We will learn about inverting amplifiers later. It's a very simple circuit. So this is the invert button that you have there. All it does is whether the signal comes out directly or whether it comes out through a inverting amplifier. So this is the invert button. It decides where it is connected, right? So that's that. So you know now. Chop button, you know what it does. You know position button. You know the mode button, mode selector. You know how it happens. You know the volts per division control, how it happens. You also know the AC, DC, and ground. Okay, all these things you know. You also know the operation of time per division. Right? Out of all these knobs, those are the most important ones. But you know all these now. In addition, there is this variable, right? So variable thing. So we are what this does is basically it changes the gain setting. Now in this mode you jump from one setting to another, right? In this using these knobs, it jumps from one setting. So you have volts per division. So the gain can be 1, 2, 5, 10, 50, 100, likewise, right, up to 5,000 or something. Now while it is at this position, if I rotate this thing over here, this button over here, this knob over here, VAR, what it does, it varies between this and that. It's no longer 5 or 10. It's something in between depending on this position of the knob. So it's kind of like varying the amplification, right? So it's kind of like, you can look at it like between this and that you have another amplifier whose gain is controlled through this small pot. This is actually a potentiometer, right? Something like that. Okay? So by doing that, so make sure. So therefore, if you do that, what happens is what you read will be different. Instead of 5, it will be like 7.5 or something. Then what you see on this time per division, it will not be equal to 5 volts per division. You don't know what value it is. It's something in between. So therefore, if you want to make voltage measurements, make sure that you always put this variable position onto this calibrated position. CAL stands for calibrated. Once you put it there, it ensures that the gain and therefore the voltage per division is ensured by this setting. Okay, is it clear? Yes. Yeah, so make sure that you have to do it. Otherwise, sometimes if it's moved, you don't know what it is. So now I'll show you one of the signals that's available in the circuit itself. Let's put it to 1. See, now this, you can read this if needed. Let's see if I can focus this. It's hard to focus, but the value it says is 2 volts peak to peak. So the peak to peak value is 2 volts. Now I have put it into 1 volts peak, right? So this volts per division is 1. You can attest, right? So this is 1 volts per division, right? Okay, come and see. So this is 1 volts per division, right? This, yeah. And what does this say? 2 volts peak to peak, right? So therefore so you see that it is 2 volts peak to peak. Now what happens if I change this? See what happens. See what happens. Now it's no longer 2 volts peak to peak, right? Not because my source has changed. Source is still 2 volts peak to peak. But my output screen does not represent this 1 volts per division now. Now this, in this case, that's like about 0.8 of a division. 0.8 division is equal to 2 volts. Yeah, if I want this to be 1 division per 2 volts, it's like that, right? So therefore, whenever you make measurements, voltage measurements, make sure that you have it exactly at the cal position. Otherwise, your measurements will be wrong. Is it clear? That's something that is very important that you need to keep in mind. Always check whether this position is in the cal position, right? Both these channels, right? Okay, so you know the operation of this cal. Both these are similar in 2 channels. That is the same. So you know how it works. And this, obviously, you have seen this small hook-like thing that you see on your oscilloscope. Sometimes it's in this corner, sometimes it's in the middle. You see, for example, here in this, you have it here, right? So different oscilloscopes have it in different positions, but this small metal hook-like thing, that basically say, and along with that, it says what is the output. It's a calibrated signal. It says sometimes 2 volts peak to peak, 1 kilohertz. Sometimes it says 0.5 volts peak and 1 kilohertz or 10 kilohertz or whatever it is. You check your oscilloscope, it will say that. So it guarantees that that's the signal that comes out of it. It's a square waveform, just like this. Okay, so you should see something like that there, and you can use that to see whether your measurement is correct. Actually, it should give you that value that it says it has. Okay, so if you have this calibration off, you will see that it doesn't give you that value. Okay, so make sure that you have it there. So you know all the buttons in this section, right? The vertical section, you know all the buttons, correct? How they work, what it actually does in hardware, correct? Yes? Any questions for that? You will actually see these circuits and things like maybe in block diagram form in actual theory section, but you need to understand this. It's very simple, right? It's not hard. And also you know this time per division, the sweep controller, and also that also some has magnification next, a magnification button, which means if the sweep rate is 10, you are amplifying it faster, right? So the slope is 1 division per second. It will be 1/10 of a division per second. So it's faster, right? Slope is 10 times high. Magnification by 10 is that. And also there is another one, XY mode, right? This XY button. Sometimes it's in the XY mode, separate one. Sometimes it's in the time per division. If at the end of the time per division dial, you have XY position. Obviously, when you put it into XY position, what it does is, instead of connecting the sweep signal to the X controller, X electrode, you connect the X electrode to channel 1, Y electrode to channel 2. Okay, so instead of this one being connected to the sweep signal, this is connected to channel 1, and the other one connected to channel 2. Right? Clear, right? It's clear. So that instead of with time, what it draws is between X and Y, channel 1 versus channel 2. Channel 2 versus channel 2. Channel 2 is Y, channel 1 is X. Okay? So that's all it does. So you know this operation of this also. Horizontal position. Horizontal position is similar to the vertical position, but that applies this DC voltage to the X plate, right? So it will move in the X direction. So it will. So what will happen? See, if I move this, the starting position changes, right? You see that? Right. So where it is, so instead of this being, now when I apply 0 volts, it doesn't no longer start at this 0, right? So when I apply this, that means I have, this should have been, now this is the 0 volts, now I am applying a positive voltage here, that's why it has moved, right? So that's the Y position control, that also you know now. This button, you know, X magnification, you know, XY mode, you know. Again, here you have another calibration knob. This one is also for this. So if I uncalibrated it, you will see. So now sometimes you have another button to make sure, if you want to go into this uncalibrated mode, the variable mode, you have to press this uncal button, right? So then only it will change that Y sweep. Otherwise, if by mistake you change it, it will not, right? So you put it there and see what happens. Now the signal has not changed, but I can change the time base, right? So what that means is, it doesn't, now if you do this, if you take it out of calibration mode, what that means is you cannot use this dial to figure out what exactly is the time per division setting, right? Is it clear? So in order to make time measurements, if you are making, now earlier I said if you are making voltage measurements, you have to ensure calibration position is there in the vertical commands, vertical channels. Now, if you want to ensure you are measuring the right time information, that is x-axis, you need to ensure not in the XY mode, in the x-axis, you have to make sure you are not in the uncalibrated position. You have to make sure that this is not pressed. Some cases it's not pressed. Sometimes you have other oscilloscopes where it's like you can uncalibrate it by I don't know, some people may hear it around here. See, you hear it when it is, there's a click sound when it goes into calibration position, and when it comes out, you don't, so you know that it's not there. So now it's there. So in this case, what you have is pressing a button to make sure it's uncalibrated, and then you can change it. If you have it uncalibrated position, no matter how you change this, the trace doesn't change, right? Only if this is pressed, this will change. Okay, right? So make sure you have this not pressed when you are making measurements in the time direction. Time measurements, make sure that is calibrated. Voltage measurements, make sure X and Y channels are calibrated. Otherwise, your measurements will be wrong. Alright, so you know these functions now. So you know all the functions in the vertical section and horizontal section. Okay, and how they are inside the oscilloscope physical, right? The circuit level. Right. Now there's another section called the trigger section. This is the last section here, right? Now let's see what that means. Okay, I'm going to erase this. We are going into an important section now. Triggering. I think the hardest part, students find it difficult to use oscilloscopes. Is triggering, and it is actually not so hard if you understand what triggering means. Okay, so that's what I'm going to do now. Now I said, if this is my screen, oscilloscope screen. Now what happens? I have x-axis control, which basically sweeps across the xy plane and comes back, right? So when it is grounded, my y-axis is not in action any longer. It's just 0 volts applied. So what it does is it just draws a line along this, comes back, draws a line along this, comes back, draws a line along this. This is like grounded, something like that, right? So it keeps drawing on the same location, right? So this is basically what we do when there is no signal applied or ground. Now what if I change this, remove it, and I connect it to a signal, right? So what it does is it draws across this according to the input voltage. In this case, what you have is a square wave. What you have here is a square wave. What you have is a square wave. It's a square wave, and it keeps drawing it, right? Now what will happen if, okay, let's assume I draw the square wave. Now square waveform is a little bit less tricky, right? Let's move to a sinusoid. Right, so I'm going to connect this into a sinusoidal signal, right? See, now I have a sinusoid like that. Right, it's a sine signal. Now what it does is my y-axis, basically I'm giving a sinusoidal signal. So it moves like this, right? Constantly moves like this, right? Up and down, up and down, up and down. Nothing else. But at the same time I'm moving it across my y direction. Like x direction, like this, right? So while I am doing this, if I move my screen across my screen, it will draw my sinusoid. Come back. When I am coming back, I apply very low voltage so that you don't see the signal. It's doing something like that, right? Now, what happens if I try to draw it here? Right? Okay, the first time, let me draw this sinusoid. It stops here. Now it goes back and comes back. It takes a finite amount of time to come back here, right? Let's say by the time it comes back, it is right here. Right? Let's say at that time, when my cursor or my pointer is at left corner, voltage is at this point. If I start drawing again, what could happen is it will draw like this. And after a while, let's say if this is what the voltage is when I come next side, it will draw again. Like that, right? So every time you start at a different position, right? Now if this persistence is still there. So the first one that I drew across this is still there. Let's say it only took 5 milliseconds to go from here to there. So this is like 1, 2, 3 cycles. Let's say 3 milliseconds. One cycle is one. So 1, 2, 2.5, or maybe let's say 2 cycles. Let's say if I'm using 1 kilohertz, it will take just 2 milliseconds, right? 2 milliseconds, obviously that glow will be there, right? So all these 3 lines will be there within that 5 milliseconds or 6 milliseconds or whatever. These lines will be there. So therefore, what you will see is something like this, right? So you see everything there, right? You see? You see all these different phases you see on the line. This is not what I want, right? If that is there, I can't make a measurement out of it. So what I want is for this to wait, we come here and wait until it starts from here. So it waits here until the voltage level of this signal reaches, and now the voltage here will be like that, but you don't draw, you don't start sweeping across it until it comes here, right? So you wait. So now sweeping is like this, right? And then this is going back, and you need to wait this long until you start sweeping again, right? Correct? If that is the case, then what I will be doing is I will be going like this, waiting, and now starting only at this point, and then drawing on top of this again. Okay, now it should be better, right? So that you won't draw all sorts of different phases at the same time. Now one problem though is, what will happen if I am right at this point? Then my position is still there. Now I have reached my target voltage. Then I will start drawing. This is what I would see. Instead of this, all these things, I would just say unfortunately this is kind of like just two phases, 180 and 0, only those, right? You will see just 2 phases, not all the running things, but just 2 phases. You will see there. That is also not good. So to avoid that, what we do is, so this comparing the level. So at what level you start drawing? There is this called trigger level. There's a knob called level, right? This, so you will see trigger level. If I move it into one side or the other, it will start running, right? Like this. In between, so you see in between. Now I'll move it this way a little bit. So this is where it starts. Now the trigger level is this. As soon as it reaches this level, it will start drawing. So if I move the level, see, it waits until it starts at that level. Now what happens if I go beyond that? See, so you see it starts at different levels. Now there are 2 ways to avoid this. You put it into normal mode. Now this is in the auto mode. So if you press it again, now it will indefinitely wait until it reaches that level. Now it's not reaching that level because level is high, right? Now if I change it quickly down, now it is reached every cycle. If it goes beyond, now it goes beyond, it will not draw, right? If it draws, and again like that. If it goes below that, again it doesn't draw it. It waits until that voltage is there. As well as the direction. Now there is another one called direction. Slope, right? This one right here, the slope button, right? Plus and minus, right? So if you, now it is in the up position, which corresponds to positive. If you press this, it's a negative. So that this is going down. It waits until that voltage is reached. and the slope is negative. See, the slope is going down now, right? Is it correct? Yeah, it waits until it reaches that slope as well. Okay, only if it reaches both, because otherwise at this point also it reaches that level, but it doesn't match the slope. Now I need this negative slope according to this setting, so it doesn't achieve that. So therefore, that's why this waits still, right? So and this waiting time is basically what is controlled for that. There is a comparator. You will learn this circuit later on in the second year, in the next year and next semester. But how long you wait? So you wait. You compare it to the level that I have. So you have a comparator. This is the level that I set. This is the level setting. So level setting is something like this. So you have plus minus voltages, and then this is the signal itself. Signal itself comes here, and output is what controls this sweep signal. It switches on and off based on that. It triggers. What it does is it actually sends to a trigger. So when it triggers, so it's basically something like this. It produces triggers. As soon as you receive this, it produces a sweep and waits until it reaches another trigger. And the slope is determined by time per division setting. Okay? Clear? Everybody clear? Right. So that basically covers the sweeping. So and triggering. Right. Now you know if your signal doesn't, like, if it doesn't get triggered. Triggering means you have a stable signal. That means your signal level, the trigger level, is not correct. Right. It has gone beyond your signal level. Signal is varying somewhere. Your trigger level is outside. Trigger level is outside that thing. So if you put it to auto mode, it will wait for some. Now in the normal mode, it will wait indefinitely until it reaches that voltage. That is why it doesn't grow. In the auto mode, it waits for some predefined hold off time, which is controlled by this hold off switch control, and then start growing again. Right. The reason why it doesn't stop is because it starts at different levels after this predefined hold off time. Right. Depending on the hold off time, now it's drawing faster. Now if you make it, if you increase it, it will be different. So how long you wait until the next, without waiting until it reaches that voltage. Right. So that is that. So you have this untriggered signals. This is the issue, right? So therefore you need to make sure that you lower the trigger level or take the trigger level to that signal level. Okay, right. Now you know the level operation. Operation of the level, hold off, auto and normal mode, as well as lock. Lock means, see, once you have that level, it wouldn't. So it couldn't go beyond that. So even if you change this, it won't affect it, right? So it's automatically setting the value, and you are not changing it at that value that I set lock. Okay, if I change it and put it again, it will be a different value, right? Right. So it's actually 0 and negative, 0 and positive, and 0 and negative. So in the lock mode, okay, 0 will be the level. Okay. So you know this operation, this operation, this operation, this operation, and also the source. Source for trigger. Again, now I said it's waiting until it's reached, right? So this comparator looks at a certain signal and to see whether it has reached that level, right? What channel is that is what is selected using this trigger source. So whether it is channel 1, if it is channel 1, you wait for the signal to reach from channel 1. Now if I put it to channel 2, it will not get triggered because it will not hold on, channel 1 DC, normal mode, channel 2 ground, hold on, channel 2 not locked, this is normal mode. It actually should not correspond, it should not trigger actually, because the channel 1 does not, channel 2 does not have a signal. It should not. Let's see why it triggers. Okay, the reason why I had that was now it doesn't trigger, right? Channel 2. It should not, according to okay. This is line, channel 1, channel 2. Okay, sorry, I have pressed the alt button because alternate. Now there's another button here. I'll explain why, what happened. Okay, now when I said when I have it at channel 2 and I don't have any signal in channel 2, it should not trigger, right? Now that is what's happening, it's not triggering. Now if I press this button here, it triggers because it says alt, which means it changes the source alternatingly every cycle, right? You draw one, you look at channel 1 until it reaches that level and slope, and then trigger it. Come back, wait for the channel 2 to reach that level alternatively. Okay, alternatively you go back and forth. So therefore the reason why it triggers now, though there is no signal in channel 2, is because once you sweep, you come back, wait for the channel 1 to reach that value. It is not there, but in the next cycle it goes back. Sorry, channel, you wait until the channel 2 reaches, it's not coming. Next cycle it checks the channel 1. Now it reaches, draws it. That's why. So if you remove this, it doesn't draw, right? Again, if you go to auto mode, it will draw, but it will not stabilize. That's why it's running. It waits some predefined time defined by this hold off value, and then it starts drawing again. It's not triggered because its value is not there. Now there's another one, so that is trigger mode, whether it is channel 1, channel 2, or line. Line means the 50 Hz signal. It's powered by the line, right? 50 Hz, 240 volts. It has a AC signal, 200. So this signal is 240 volts, 50 Hz. So the 50 Hz signal, you look at it, you make sure you attenuate it so that this level corresponds to the maximum and minimum levels of this screen. So let's say 0, -5 and +5, let's say, and then you define the value and the slope. So if I put it to line mode, again it doesn't, it's again running, right? It's not stable. See, the start point is not the same because the start point is selected from the line, the AC voltage. Now if I change this voltage to 50 volts, for example, 50 Hertz, see, now it's kind of stable, right? But you see the start point slowly changes. See, this trigger level slowly changes. That means my power line frequency is not exactly 50. I can see what it is. Sorry, 50. Hertz, and now I'm going to change this value. This is basically, I'm going to change the frequency here. You see, now it is still changing. I'm going to increase it a little bit. It's going the other way. Decrease it a little bit. It's going even faster. So this is like somewhere between 50 and 51. So now it's very almost stopped, but it is not, right? So if I increase in 51, it'll go faster, 50.01, right? It's not 50, but it's not 49.9, so it will be 50.05 or something like that. I don't have the precision to control it at that level. Okay, you understand what's happening? So this is basically why it can be triggered is because this signal is also 50. The signal that is being used to trigger the signal is also 50. So therefore, if their frequencies are identical, you can actually do this. Okay, so you are using a signal that is almost the same frequency as my signal that I'm looking at. It's a different signal, but almost the same. Okay, right. So right. So we know the operation of the trigger, and then there's also another one called external. So there's this third BNC connector. That's the external signal. So if you want to connect a separate, it's not the channel 1 signal, it's not the channel 2 signal, it's not the line 50 Hz signal. If I want a separate signal which is similar to the signal that I have, same frequency, then and a clean signal, then I can use that to trigger it. A third, completely third one, external. So that's the third one. So you understand that also. So trigger source is basically what is used for this, whether it is channel 1, channel 2, so channel 1, channel 2, this is channel 1, channel 2, this is external, and line 50 Hz. So depending on that, what am I looking at until the signal reaches that level is determined. Okay, so that's that. So you understand this. So there is only one thing that I have not explained, this coupling, right? There's this other thing called coupling, right? Coupling is again the same thing. How am I connecting this to that comparator? Trigger source connected to that. Now here there is DC coupling, means I am directly coupling it. So channel 1, channel 2, channel external and live, you are connecting it through a switch which you move. And DC coupling means you are directly coupling it to my amplifier. So direct coupling. So that means like this. AC coupling means through a capacitor. Then I'll be pointing it like that, right? And then there's this high frequency reject, HF reject, and TV, right? Those two settings are also high frequency reject, means you have this setting is there's a capacitor to ground from this. You connect it like this. So you have this connection. I can move this. Channel 1, sorry, not channel 1, the first one is DC, this is DC, this is AC, high frequency reject is something like this, so that high frequencies will go through this capacitor and short circuit into ground. It will not get the high frequency noise will not get to the comparator. The last one is TV. So for TV signals, there are vertical and horizontal signal specifications. So if you are using oscilloscope to diagnose those, you can use that setting. We are not going to talk about that. It's out of the scope of this course. Okay, so it's also for a specific application. Okay, so we know all these buttons and how they work. Is it correct? Now any questions? Now with this you should be able to comfortably handle an oscilloscope to make correct measurements. Right? You should be able to stop this running you need to know which setting you need to meddle with if your signal is running, whether it is the, so if the signal is not stable, then it should be the trigger command that you need to use, whether it is the level. The first thing that you would touch is the level. See whether the level, by changing the level you can stabilize it. If it still doesn't do it, then you have to go to see whether you have used the correct channel, the same as the channel that you are trying to stabilize. Channel 1, you use channel 1 to stabilize trigger, or else you can put to alt mode, which case alternatively it will come back, so it's the same as that, but better option is going for channel 1. And also sometimes this can happen if your signal is noisy. Say for example, see now you see there's a signal which is kind of noisy, right? It's not that very clean signal that you saw earlier, right? Can you see? So because it is not so clean, even though you are using the same channel to trigger it, it's running here and there because the signal itself is noisy. Signal itself is noisy. So if my signal itself is noisy, so my signal looks like this. So I set a level and a slope, let's say positive going. So as soon as it reaches this, it starts growing. Next time it may start from another point. Say for example here, that also starts at the same voltage and the direction is positive. So it may grow like that, right? So when the signal is noisy, you may not be able to trigger using that same thing. That is why you have this third option of external triggering. If you have this external triggering mechanism, now you see it's not, you cannot trigger it. No matter how hard I try, I cannot actually trigger this. The reason for this is my signal itself is noisy. Obviously, theoretically I cannot trigger this. For this, if I want to do this, I can use another signal, like for example 50 hertz signal. If this were a 50 hertz signal, then I could have triggered it. Say for example, let me put 50 hertz. See, much better triggered, right? It still jumps around a little bit, but always starts from the same point, right? So now you see the same phase, right? The phase doesn't change anymore. Earlier, if I put it into channel 1, see, the phase changes time to time. You can see that, yeah? That's because you have the signal itself is noisy. So that is why you have this option of using an external trigger. If now I have another signal source, signal generator with 50 hertz or whatever the other frequency, I can stabilize this. Okay, so you are not waiting until this signal reaches that level. That's the clean signal. I am waiting until that. So therefore, I always start with that. So you may have noisy signal, so you draw something like this, right? The next time it may be noisy, but it still has the same phase. Next time it has the same phase, noisy. So after a while you will see kind of like thick line, just like what you see here. This is thick line not because the voltage is, the signal is thick, but because you have multiple lines appearing on the same signal. So if I increase this, you see different lines appearing. See, different lines appearing, you can physically see. See, you have different lines. Yeah. Okay. So that's basically all you need to know about an oscilloscope. But there is one more thing that I'm going to tell you about this probe. About this probe. I think that part is also there in your experiment. If you look at these probes, there's this small piece of thing that you can move front and back, right? And it says into 1 and into 10. You take one of these probes and see this part here. You see, you can see it can be different in different probes, but somehow there is a small thing that you can move forward and backwards. Now, so far what we have used is a into 1 probe. That means whatever the signal that you give into the tip goes to the end of the probe, to the other side, right? So to the other side you have the same as the tip. It's 1 to 1. It's a conductor. But there is this other connection which is called the into 10. What that means is you have to attenuate the signal by 1/10. 1/10 of the signal. Say for example, if you want to measure the 240 volts signal, you can't just connect it to the 240 volts, because you can connect. In this case, it won't cause any problem, but you won't see the signal. Even if you put it into 5 volts peak per division, what you can see is only 20 volts peak or 40 volts peak to peak, not 240. So you will not see the signal. To see the signal, you need to attenuate the incoming signal. To attenuate the incoming signal, use this thing. What you have in there is not just. So how do you attenuate? So voltage division, right? If you have 240 volts, if you want 1/10 of it, here I want 1/10. So this is V1. I want V1 divided by 10. Correct? So what is the ratio between R1 and R2? Let's say R1 is equal to 1 mega ohms. What should be R2? Can someone tell me? This is your first opportunity to get 1 point, the bonus points. Quickly make this calculation and tell me. The first person to tell me will get 1 point out of 100. So that means you already have, you can score 101 for this course total. Anyone wants 1 point? So if you are in a borderline, you will be pushed to the other side. This is big. Anyone who has the courage, raise your hand and tell me. What is the value of R2 if R1 is 1 mega ohm? It's a very simple mathematical operation that you need to do. What I want is V1 is there. I want 1/10 of V1. What's the value? Anyone? No, nobody. From that bench? No? No one wants this 1 point? I'm going to tell in maybe 10 seconds or so. Anyone? This 1 point is big. Think of it like this. The final exam, the total 100 points is 50. Right? 50% for the final exam. So that means 2 points in final. 2 whole points free. You just have to tell me this answer. Nobody? I'm going to tell you, na? and you are going to jump into Mahaladri or something inside because you couldn't do it. This is voltage V out is this is V in, this is V1, right? Let's assume this current is I. What is the I? I is equal to V in divided by R1 plus R2. The same current flows through this I, because I am not taking any current here. So therefore, output voltage V out is I times R1. This is I times R1 is equal to R1 over R2. This is the ratio times V1. We put this V1. So this is not. So this is I. This is equal to V out. So therefore, this is 1/10. Say 1/10 is equal to R1 over R1 plus R2. R1 is 1 meg. 1 is 1 megawatt. So therefore R2, 1 plus 1 meg plus R2 is equal to 10 megawatts. R2 is equal to 9 megawatts. Is that hard? And actually you don't have to do all this math. It's voltage division, I think you should know intuitively. So if I put R1 is equal to 1 and R2 equals to 9, whether it is mega, kilo or whatever it is, that ratio is all what matters. And you will get 1/10. So this is basically what you have there. But in addition, but this unfortunately, now this 1 meg is, where's this 1 meg come from? 1 meg is not physically there. It's the input impedance of this device. Okay, so my oscilloscope, I said I have this thing, it's connected. So between this pin and this, okay, so that's these two. This is connected to the chassis. Between this and that, what you have is an impedance. It can be modeled as this. It has a specific resistance. It is designed to be 1 mega ohms, and it has a capacitance value. Typically it says what it is. If you look at this thing, it says 1 mega ohms, 2.25 picofarads. Can you read this? You can see in your one also, it says right here, you can check and confirm, right? It says 25 picofarad. So therefore, there's a 25 picofarad also. So this is 25 picofarads, 1 meg. So now, what I'm doing is, this is basically, so it's not just this. Now, the probe has this. When you put it into 10 mode, what you do is, instead of connecting it here directly, I'm connecting through a 9 mega ohm resistor. But unfortunately, inside this I also have a capacitor, 25 picofarads. So what about that? Now, I said high frequencies. At very high frequencies, capacitors are like short circuits. They like to go through. We will learn this later, right? But resistors, they don't care whether it is high frequency or DC. The same thing. They will be very faithful. Will be the same value. But capacitors are not like that. Higher the frequency, so the more money you have, the looser is the low. You just let go. Okay. So you see this all the time, right? Right. But the poor people, they are subjected to the law to the letter, right? So likewise, DC, no, you can't do. You don't have money. But when you have a lot of high frequency, you just let go, right? It's like that, right? So these capacitors, unfortunately, what happens is very high frequencies. When you have this setup, it is not 1 mega ohm. This 25 pico, most of the signal will flow through this, and this would look like a short circuit at very high frequency. So therefore, at high frequencies, it will not be 1 to 10. This will be severely attenuated. This will be, let's say, 1 kilo ohms equivalent resistance. So then what we will have is 9 mega ohms to 1 kilo ohm. So if you put it into that equation, 1 kilo ohm divided by 1 meg plus 1 k. So this 1 k with respect to this is negligible. So this is 1 k, 1 meg, this is 1000. So instead of 1/10, now I attenuate it 1000 times, right? It's not good. And with worse still, different frequencies you will have different attenuations. This is not good enough, right? So therefore, in order to make sure that for all frequencies I have this 1:10 ratio, what I have to do is to ensure that at high frequencies I have another path for my signal, which is, if this is 1 kilo ohms, it should be 9 kilo ohms, right? So there should be another path that is 9 kilo ohms. So instead of the signal flowing through this, having to flow through this, it will flow through this. And now these two still have 9:1 ratio in impedance case, impedance wise, right? So if this is picofarad, typically the impedance impedance, so we call it as Z, is proportional to 1 over capacitance. Higher the capacitance at a particular given frequency, lower the impedance. Right? So therefore, if this is 25, I need to have 9 times less capacitance in order to achieve the same effect, right? So 25 divided by 9, is it right? Then only so resistors you have R1 over R1 plus R2. Capacitors you have C2 over C1 plus C2. Okay, it's the other way around. Okay. So if this is 1 into 9, this has to be the other way around, right? So this will be, I'm not sure whether I have written it right. So I'll give you the equation and then later on you will learn it. Impedance of a capacitor is equal to 1 over 2 pi f c, right? Whatever the frequency, right? So let's say Z1 is this, Z2, so this is 1 over 2 pi f, C1 is 25 picofarad, right? That's the impedance of this particular capacitor. C2, the value that I need to put there should be so such that C1 over C1 plus C2 is equal to 1 over 10, right? So again C2 therefore should be 9 times C1, the same as R, right? This is the impedance, not the capacitance. So therefore 9 times is 2. So if I replace this is 1 over 2 pi f C1. This is 1 over 2 pi f C1. So therefore I can get rid of this. C1 should be 9 times C2. So therefore C2 is C1 divided by 9. So this is 25 picofarad, 25 divided by 9. Correct? If this is the case, at high frequencies also, you will have the same kind of ratio. In between frequencies, they will have a combination of impedances so that the total impedance will again be C1 plus C2. This is basically both these, okay, will be equal to 1:10. If I ensure this. Now the issue is this, I can very nicely control this. Once it is there, it's there, very precise. Capacitances, however, change with time, with temperature, humidity, all sorts of other things. So therefore this 25 picofarad may be there, but in between this and that, there may be parasitic capacitance. This I can control, but the probe, you have parasitic capacitance, right? You know, between 2 points you have some capacitance. So because of that, this value may change. Because of that, if you don't have a particular value there, it will vary. So therefore what happens is, it will change with time, and it will not produce the same attenuation for all frequencies. Different frequencies, it will be different. That's not what we want, right? What we want is, for all frequencies we want the same attenuation, 1:10. In order to do that, we have to ensure that this capacitor is variable, so that I can change it so that I can achieve this 1:10 ratio. And this is the purpose of this small thing that we saw earlier. This the square waveform that I showed you earlier. It is given for that specific purpose also, in addition to calibration. So if I plug it here, so you see this 2 volts peak to peak signal is there. Now my probe is into one mode, so therefore it's just, there is no attenuation at all. So the whole thing is there. There's nothing to worry about. But if I put it into 10 mode like this, and I increase this by a factor of 10, right? Now it looks like this is good. But what happens is, probe tune this is something that I think we have tuned. Let me use another probe. This is better, right? See, now this one, you don't see a square waveform, do you? See? Right, now you see the reason why you see this distortion. It's not a square waveform. Do you see this as a square waveform? This is a square waveform. It's not a square waveform. It's kind of like this, right? It's what you see is something like, so what it should have been is this. What you see is something like, now I'm drawing this because I know it should be like that, okay? So it's like this, right? So this is what you see. Now the reason for that is, at high frequencies, these are high frequencies, edges are high frequencies, these are low frequencies like DC, right? So at high frequencies, the dominant factor is the capacitor. So the capacitor decides what this voltage ratio is, and decide what is the initial voltage of this signal. At DC, the resistors decide what the ratio is. Okay, so it comes to this, because we already know that it should be 10. Right? So therefore it achieves it. But because their ratio is, capacitor ratio and resistor ratio both are not 1:10, we have something like this. Now in this case, the resistor ratio may be less. Sometimes the resistor ratio may be higher. In that case, I may even see something like a signal like this also. Okay, I can even see a signal like that. See, now capacitor ratio and resistor ratio are different in the other direction. Now it's in the opposite direction. Now there's this variable resistor on this probe. There's this small hole, and then in that you have a small variable capacitor, right? Okay, so inside this, so there's this hole. You can see sometimes it's here, sometimes on the probe itself, sometimes it's on the probe. Okay, and once you do that, you can actually tune it until you see a square waveform. Okay. So now it is tuned. Now we are ensuring that capacitor ratio and the resistor ratio is the same. Okay, understand this. Now later on you should be able to prove all this using the analysis of circuits. Circuit analysis you should be able to do it, but right now we are not expecting. Later on you will learn how to do it. Okay, so that is why you have this tuning, probe tuning. This is called probe tuning. Unless you, now this is only applicable if you put it into 10 mode. Into 1 mode you don't have to do probe tuning, right? Any probe will work into 1 mode. You don't have to do any, you have to worry about that. But if your signal is too large, then you have to make it smaller, right? To get it into that voltage range of the oscilloscope, then you need to have into 10 probe. And if that is the case, if you have only one frequency, then you don't have to worry too much about it either. But to get the exact value, you need to know that its value has to be that, because otherwise you may have a variable attenuation depending on the resistor value and the capacitor. So therefore you have to have a tuned probe to make measurements. Okay? This is called probe tuning. It applies when you have large signals or high frequency signals or multiple frequencies. These square waves have multiple frequencies. Fourier spectrum, I think the first year Dr. Vijay Surya talked about this, right? Spectra, when you sing you have this, or talk, you have the voice signal, you decompose it into different frequencies. I think you did something like that, right? Did you not? In 108 or something, 108 or 118 or I can't remember the code, but I'm pretty sure you did. Maybe you forgot it already. This is basically if you are using that high frequencies, so bandwidth of frequencies, you need to have this. Okay. All right. So any questions? So you will have to do this in your lab class as well. Any questions? Please ask. Okay. This is the next opportunity for you to get points. Okay. I'll give you half a point for every question. Now earlier I gave one point. Now I'm going half a point. At least anyone who is enthusiastic in getting extra points? Nobody? Everybody crystal clear, or don't understand anything, or afraid of asking questions, or what? Remember, when you are working with me, you have to interact with me. Okay, so remember, you can't escape that. I am going to come to every single person personally, right? During the lab classes, I am not going to teach you anything. I am going to come to you, sit with you, and talk with you, and ask what is your name, where are you from, and all sorts of other funny things. And as I said, you will have to come up with something that I can remember you. Okay, so therefore there is no escape. You will have to talk with me. So better get points for talking with me, right? Yes, if you are talking with me, irrespective of what you were asked, what you were instructed to do by others, you have to talk with me. I'm going to come and personally ask. Then you can't say, you have to talk. Then why don't you ask questions also right here? No questions? It's your opportunity, okay? No questions? Okay, and then I'm going to conclude this lab. If you have questions from this, better to ask. There is no, you don't have to submit any coursework here. This is all for your knowledge. That's why I am giving you this opportunity. I'm doing this for your knowledge. You should be able to understand how this oscilloscope works, why, if you are making a measurement, how to make sure that the measurement is correct. All that is important. That's why we are doing this. And if you have any doubts, this is the place to clarify it. Okay? Any questions? No? Not a single person scored a single point. I'm very disappointed about you guys. Honestly. Every time, every other batch, at least one person asks some kind of question. No? Nobody wants to ask? Everybody understood everything very clearly? We'll see that. I'm planning to have a practical exam. We'll see. And if you don't ask questions, I will ask questions. Okay? Alright. Anyways, maybe after a couple of days you will get familiar with my style and you'll start asking questions, hopefully. Or maybe I'll get used to your style and not ask questions or expect you to answer or whatever. We'll see. We'll come to a convergence sometime. Anyways, good luck. So one more thing. When you are connecting the probes, make sure that you don't rotate or turn the knob using this plastic. Only use this metallic part, right? Just otherwise you will break the probe. These probes are very expensive. One is something like 18,000, maybe a couple of years, maybe 3 years back. Now it should be double that, no? It's so maybe 30,000-40,000. These are very expensive devices. Please remember, you guys are, this is free education. You guys are fighting for that, no? We don't get any money to purchase these days because of the economic crisis. Even before that, that was the case, but now zilch, nothing, right? So therefore, it's your duty to protect these and make sure that your next batch and the batch after can use these. Otherwise, we won't have enough resources to buy these, right? So therefore, please use this equipment properly. If you don't know how to use them, we are ready to teach you how to do it. If you don't, you ask, we'll help. So otherwise what will happen is, like for example here, this sen is broken, right? It has been something similar to this. It's broken because it has been used improperly, right? So therefore make sure you use them properly. If you don't know how to, please ask. And we need to give this to the next batch, next generation also, because these especially these analog oscilloscopes, they are not available freely these days. Earlier these were the ones that were available. Now these are not available, but you can buy digital oscilloscopes very, relatively cheaply, maybe 100,000, 200,000. So these are much expensive than that, right? So please use them with care. Okay. All right. Thank you. So, and also feel free to come to the lab and use these devices whenever they are free. Okay. If you have free time, if you want to use this and say, come and use them, that's okay.